Wir gehen weiter im Text. We will going on. And the next is Dr. Tetsu Yoshimitsu von der JAXA. You are very welcome here in Bochum Observatory. And it's a SLIM LEV-1 moon landing mission. That's your part.
Thank you. Thank you. Hello, everybody. So it's my pleasure to be here. So since this observatory, you know that was a moon lander actually landed on the moon this January. Japan launched several moon landers, but that was the first successful one. And this observatory, this antenna, observed the radio from the moon. And we are very interested in your activities, and that's why. And there are several. So you have actually broadcasted in YouTube about that, and it was very interesting. And we are also looking at your YouTube from our operation room, also. And so I have to say thank you to all of you here. So I want to explain, say about that kind of moon lander. And in our side, I'm a payload engineer, and we installed a small robot to that moon lander, which is called LEV-1. And I am a primary investigator of that rover. And of course, that two spacecraft, SLIM and LEV-1, use the S-band radio also, and this observatory tracked both radio and what happened? So this is the appearance of the LEV-1 payload. LEV payload. So LEV-1, LEV-2, there are two rovers installed in this payload, and I am in charge of LEV-1. LEV-2 was developed the JAXA people, not JAXA people, but LEV-1 was developed by the joint project team with JAXA academic side and the university people here. One of the professors is also here. And LEV-1 is clearly seen, but LEV-2 is inside, so you cannot look at in this picture. But in any way, this is the actual shipment, appearance to the spacecraft. And so let me review the SLIM spacecraft itself. So that's 700 kilogram spacecraft in initial space mass. But it was not so large, but including the 500 kilogram fuel. And it was launched in September 2023, and landed on the moon this January, 19th January. And this spacecraft was dedicated to make what is called smart landing. Smart landing means that the safe and soft landing, of course, and we use the images on the moon surface to track the pre-planned trajectory onto the moon. And the second one is a precise landing. So we use also imagery. Precise landing used tracks the pre-planned trajectory. Safe and soft landing uses the camera image and altimeter, and we use the also images to detect the obstacles on the surface and escape, avoid the obstacle area. And precise pinpoint landing is also made within 100 meters of error. And of course, this kind of process is conducted fairly autonomously. But we are concentrated on the smart landing itself, and we did not think about after landing. So we did not thought about the long survival on the moon. So the activities on the moon after the landing was minimized. That's why we did not have so many payloads so switched on the moon surface. But 2 payloads are actually selected. One was a camera, and one is our LEV-1 payload, which composed of 2 rovers. So they are not totally interested in after landing. So they gave us just the opportunity to install the payload, but so they just took care of us before the actual deployment to the surface. After that, we have to do everything by ourselves. And this is appearance of the SLIM spacecraft from the back side. And so LEV-1 was installed there. And actually, this is upside down. So the spacecraft was mounted on the rocket upside down. Yes, you can look at the thruster nozzle on the top, but the spacecraft is going to the moon, and the thruster is onto the moon side. So this picture was upside down, but so basically our payload is suspended from the spacecraft. But anyway, so LEV-1 and LEV-2 are ejected like that. So LEV-1 was installed in a small holder, and the holder and LEV-1 are simultaneously ejected by the trigger above the around 2 or a few meters above the surface. And actual sequence was like that. So above the few meters from the surface, so SLIM ejected the 2 payloads onto the surface and makes the free fall onto the moon surface. And of course, the LEV-1 also landed. And after that, everything was made very, very independently and autonomously. And this robot hopped around the surface and generated obtained data transmitted by our installed small transmitter to the ground directly. No. And this is LEV-1. So you can look at the very big wheel, and so you can turn the altitude by rotating the wheel. And there's a hopping mechanism at the back. So there's a hopping part, and the hopping part is pulled into the body by motor rotation. And then the latch mechanism is released, and there's a spring, and the springs makes the hopping part backward and kick the surface to make the rover hop into the free space. And of course, there are 2 cameras installed, one on the front side, one on the rear side. We use the fisheye camera, and the 2 cameras cover the all the surrounding area. And we had 2 radios used to the LEV-1 to transmit the data to the ground. One is S-band, another one is UHF. We use the amateur radio frequencies for the UHF. And there is a patch-type antenna on the top side of the body. And another UHF antenna are located on the front side. That's a film antenna. Those 4 inverse F antennas are located, and we use the one rotation to activate the antenna rotation in a rotation, so we can make an left hand to polarization, right hand or something. And so actual hopping is like that. This was captured on the ground on the sand, and it was a very small video. And actually, the total distance to hop is around 1 meter in 0.5 seconds. as the surface gravity of the moon is 1/6 of the Earth, so that it means that if the same condition, in the same condition, this lever hopped 5 or 6 meters in 3 seconds. And yes. And the reason why we use this kind of mechanism is that this robot is very small. So typically we use the wheel type, mobile system for the moon rovers, but the smallest rover ever explored on the surface was 25 kilograms from the India, and this was 2.1 kilograms, so 1/10 of that rover. So the size is very small, and you cannot have a good mobile, so traversability for the small body. So we use the hopping mechanism to move over the surface on the large gravity of the moon. So actual motion is like that. I think you are wondering what kind of things after the hopping actions. So sometimes in the left figure, the front side is on the surface. Sometimes just laid down, but we have to recover the attitude to the good. So what is called upright attitude, where you can hop again, and the antennas or the solar cells are pointing upward, which means that the transmission to the radio transmission to the ground is possible. So this kind of the attitude recovery and hopping actions are so repeated, make the continuous exploration. And I have to also talk about LEV-2. It's much smaller, around 250 grams. But there's no direct transmission capability to the ground. So the LEV-2 just transmitted it's generated data to the LEV-1. And LEV-1 stored the LEV-2 data and then transmit the data to the ground. That's why the LEV-2 can be made very small. And it's almost time. So the total result of the stream landing is like that. So almost the soft landing was successfully made, and the precise landings also. But the attitude was not perfect. The attitude was upside down. But this kind of picture was taken by the LEV-2, transmitted by the LEV-1. And we have to think about say about the communication module. And this is actually the communication module here. So this is just the same one. And we have the 90 grams of the communication modes, which included S-band transmission and UHF transmission. And in the S-band, we use that kind of frequency, but the actual radiated power 1 watt. And the modulation is very typical for the space, space exploration. So their main carrier and the subcarriers, and subcarrier include the actual data in the phase modulation. And we have an actual operation bit rate is around 1 kbps. And for UHF, we use the amateur radio frequency, and the very, very precise number of the frequency, and the radiation power is also 1 watt. And we have 2 modulation methods. One is the same one for the same one of the S-band. So there's subcarriers, and the subcarrier include the operational bit rate of 32 bps, which is very small. And another one is Morse code transmission by the change of the amplitude of the main carrier. So for doing that, so I have to explain about that. Yes, this one. So there's a modulation in this. So you can change the ratio between the main carrier and the subcarrier by the modulation index. So in the space exploration, main carrier is fixed as stable as possible to track the radio, and this frequency tells the Doppler information, and where the spacecraft speed, relative speed is included. So the main carrier is stabilized as stable as possible. And there's an also constant subcarriers, and subcarrier has so broadband and include the data. And we can change the ratio of the main carrier and the subcarrier. So if you have it so higher, so in a normal situation, we use the modulation index of 0.8, which means that the power of the main carrier and the subcarrier are total almost the same. And in this, we can put the main carrier lower and the subcarrier higher. So we can change the status. So that means binary status. So and 0 or 1. And actually, when we define that when the main carrier is lower, so it is it is not a gap for the Morse code. It's dash or dot. So one dash has 0.1 second. And anyway, so so we can make the ratio of the main carrier and subcarrier, which has total of the Morse code. And it's almost the time. We use the FM transceiver and near side to listen to the radio during the debugging and development phase. So actually when the main carrier is lower, it is dash or dot, so that we can hear the sound on the right side. The actual transmitted Morse code are like that. So in the center, that's the frequency, and you can have the CQ, CQD. That's the JS1. YM is the call sign of the Lev1, and there are 65 letters, including the Lev1 status and the end PSK1. That kind of the Morse code is continuously transmitted by the main carrier of the UHF. Oh, that's the. And we correct. So you know that so we are abandoned from the mainstream of the Japanese space exploration. So we collected as many ground antennas as possible, and these are the antennas in the domestic area, and we have another antennas, and I missed the here, but anyway, so European antennas, and this is for people that are doing it. So sorry, and here in the Bossam antennas are missing. It's very near, and so anyway, so we are collected many antennas as possible, and we use the Japanese space antennas from the very big antennas for the coming from the Japanese Space Agency, which track the S-band. Since the SLIM also use the S-band, and so the antenna is pointing to the Lev1 also. It's almost the same place. And, but the real-time decoding from two spacecrafts was not possible for the Japanese antenna. So we constructed an independent system for dedicated to receive the radio from the S-band radio from the Lev1. That's the system. So we are not. It's our first time to do that. So we are not so confident about the system. So what we concentrated on the actual landing. So was the recording, radio recording. So there is only one chance, and I think we thought that the radio continued to around at most a few hours. So not so many chances. So we have to record it so radio, and after that we can process as many as possible, as many times as possible. So this kind of recording system is constructed on antenna, and S-band, but there's another university antenna, but from the so in the western area, they are also cooperative, and the antenna is diameter was 13.5 meters. That's not so large compared with here, But they tracked the S-band radio, and we so put the many instruments to make a real-time decoding by GNU radio system, and that was also successful. And so for UHF, we used the Wakayama, and so that's a little bit south from Osaka. And they also make an YouTube when the landing was made, and this kind of radio was recorded at this antenna. And from the European antennas, we used US deep space network, and typically the landing timing was not so good for the domestic antenna. So landing was made near the just before the moon set in our country. So Europe was the best area to track this stream and Lev1 radio. And, so we completely relied on the Madrid antenna from the NASA DSN. They track the both spacecraft simultaneously, since they can make an decode maximum 4 spacecraft at the same time. So the antenna is pointed to the stream, and so Lev1 is also radio tracked and decoded by them. And also the Dwingle, and so Boson is used. And both here, I think the S-band were used, and they switched the radio from stream and Lev1. And Dwingle, I think they recorded the radio file in their website, and we used their data, their recorded data, to analyze something after that. So we are very grateful for both antenna side. And what we do was so after that was we are concentrating the radio decoding, and they are radio decoded file from somewhere. And their files are brought back to our campus and processed using the vendor provided demodulator, very expensive commercial record demodulator radio system to extract the frame data from that. And of course, DSN or another university antenna made a real-time recording, and they constructed the frame data itself. And these data are combined, and so we use the PC software to make extract the actual telemetry data from the Lev1. And these are the devices, and vendor demodulator, expensive demodulator, very so yeah, actually they are very powerful. But the vendor demodulator was not so good, since the signal SN was not so good. So so we use this instrument during the development and debugging, but the actual operation, the signal is too weak, and we could not use the vendor provided instrument. So the commercial one was very powerful, and we used the maximum usage of them. But we also seeked for the GNU radio technology, and so you know that Daniel from Spain had a lot of the software open to the public, and we used the software to devise something, and finally, so the decoding was made. And we have that kind of radio and the software here, so if you are very interested in this one, so I can show you after that. And the actual motion on the surface was like that. So we obtained the maximum, we obtained 107 minutes after the deployment. After that, so actually the temperature of the robot devices went very high, up more than 70 degrees, 80 degrees. That's out of range of the electronic devices, and at the same time, the inside batteries went very completely degraded, and that's the end of the mission. And at least it continued around a little bit shorter than 2 hours after the deployment. And in 2 hours, we conformed to 7 hopping actions. And in the before and after the hopping actions, the attitude, actually we measure the accelerometer. So we have 1/6 of the G here in this measurement. So actually the robot was on the moon. And after and before and after the hopping motion, the acceleration has changed. So that means the attitude has changed by some actions. And we also estimate the actual status, whether it's on the outprice attitude or it's not a good attitude, or it's ready to hopping ready to. So we estimate the status, and that the sequence was also good. And we have radio data about the polarization. So, and that kind of data are now we analyze now, but not yet done. So that kind of data told the actual motion of the rover. So that is a very interesting thing about the use of the radio, and so we can make a cooperative work with all of you to get that kind of the interesting analyze in the future. I hope. Okay, that's the end. So yes, I told almost everything. So there are some acknowledgements of all of you, and so what is have to mention is that since we used the amateur radio frequency in UHF, so LEVAN became the first amateur radio station on the moon, and so the American people registered that kind of fact in the Guinness Book, and you can look at you can investigate in the Guinness Book radio, and that's the end. Thank you. So.
Thank you very much for your speech. And now, any questions for this mission? Dr. Yoshimitsu from the Japanese Aerospace Agency. No questions? There's one, and please in English.
Yeah, very impressive presentation. Thank you for having it. My question was, during transit to the moon, did you have any telemetry from LEV-1, or did you don't know about the status only after deployment?
Yes, so we made several operations during the flight to moon. So we used the actual US radio, and that is open to the public, and several Japanese amateur listeners tracked our radio. And we used, of course, one of the antenna in Japan, and so that is so. What we wanted to do is to charge the battery inside. So actually we had to launch the spacecraft in the so the battery is completely empty. So we want to put the battery fully charged when the deployment onto the surface it was made. So we charged the battery during the flight to the moon. So and it took around at least 25 hours. So so we have to switch. We had to switch on the LEVAN for many hours and many days, and we operated the LEVAN during the flight to the moon. Yes, and we had a chance to track, but totally it was not good since the SLIM spacecraft was rotating, so spin stabilized during the flight, so the radio was not stable. So it was very difficult to get the actual Morse code from the LEVAN payload. Okay.
Okay, thank you. Another question? There's no other question. So I thank very, very much to you, and I have a present for you. This one for you. And this certificate for you.
Thank you very much.
And this one for you. Okay. Thank you very much.